All right. So welcome everybody who joined the State of Bias webinar series for the third time. And today we will discuss the practical aspects of modeling hierarchies and how does it look like to make a transition from a regular model to a hierarchical model, and what is a hierarchy and where you can meet it in real life, and what to do if you don't know how to set priors. We will start with some really necessary basics of HMC and why hierarchy matters for understanding how HMC works. And then we will go to the example of a really toy economic model for production. And we will see how hierarchy helps to make inference on the parameters of the production model. We will also learn how to use prior predictive checks to make our models better and well behaved, and how does it help to get priors for hierarchies. When you meet Bayesian inference, then you might question, what if we have all the distributions that we can estimate in closed form? Because, well, there is a wide range of models so that you can have conjugate priors, so everything is really well behaved, and you have closed form formulas for everything. But unfortunately, in real world applications, this covers only a little set of problems, and there is literally low to no flexibility, yet they are really scalable to solve big data problems. On the other hand, if your problem is very specific and you don't have a closed form formula, then you might need a more complicated distribution which doesn't have a closed form conjugate posterior distribution to the solution of the Bayesian inference problem. And these problems are less scalable than their closed form counterparts, yet you can express everything you know about your model, about your problem and priors. And this works with very complicated distributions. And HMC is an algorithm that helps you to estimate even those complicated models which express everything you know about your data. So Hamiltonian Monte-Carlo is an evolution from an algorithm that you might meet in physics applications. So it's a dynamics model that expresses the motion of a physical object in real world, where you have a landscape with hills and then it goes down and so on. And this algorithm requires first gradients and an implementation for numerical integration. I don't say that you need to understand every bit of this algorithm, but understanding just something helps to understand where the algorithm fails to get the distribution correctly. And we will see this in our hierarchy example. So Hamiltonian Monte-Carlo works on parameters of our model, and you can treat those parameters as concatenation of all the parameters that for which you specify prior distribution, and they're called positions. The velocity is something very specific to the algorithm itself, and it helps to link the trajectories, the positions, and the motion nature of the algorithm to make the simulation of the ball. And this ball is your parameter set. The easiest interpretation I found that you can think of the algorithm is, let's say you have a skateboard field and you have a football ball, which you put in this skateboard field, and then you push it, and it goes all around this skateboard playground. It goes up the hills, then it goes down, and what it does is actually the simulation of the trajectories, the velocities it will encounter in every single point and time when you push it. And Hamiltonian Monte-Carlo will do exactly this with your parameter set. It will make the parameter set travel through the landscape of your posterior distribution, where the landscape is very deep and narrow. It will mean that there is a high density region, and the ball will stay very long in this high density region. When the landscape is flat, that means the posterior distribution has very low density there, and the ball, the parameter set, will freely travel through this landscape. So essentially, the more complicated the landscape, the more problems the Hamiltonian Monte-Carlo will encounter. And we will see how the landscape will change when we move from one parameterization to another. When the landscape is bad, I mean there is something very specific about the distribution. And there can be many examples of these pathologies. For example, it might be strong correlations between parameters where the distribution will look like a straight line. There might be funnels in the posterior. This is the case for hierarchical distribution. There can be very strong likelihood, which boils down to a very concentrated posterior distribution. Or it can be some really weird multi-model distribution. Everything will create difficulties for Hamiltonian Monte-Carlo. And as a modeler, you should try to build your model and parameterize your model in the way that reduces those pathologies. The more the better. If you want to read more about what is HMC about and see how it looks like visually, how integration paths are made, or maybe you need some code examples, then in the PDF you can find useful links on this slide. They're ordered by the level of difficulty. So the first link is the easiest one to understand, just basics. And the last one is very hardcore mathematical paper. So let's go to our example. If you have any questions to discuss about HMC, and maybe you don't understand something, you can ask it in the webinar chat. If you don't, let's go ahead to discuss the example. All right. So our example will be the Cobb-Douglas model. If you're not familiar what is this Cobb-Douglas model about, then imagine you have a production field and you have workers and they have some labor investments. The easiest form of Cobb-Douglas model will include only one production factor, labor. A more complicated model will include labor, capital, something else, and more factors to follow. And we will focus on the simplest possible interpretation of this model. We will have some groups. We will know everything, mostly everything about those groups. And we will also take into account the difference between those groups, and specifically the total factor productivity. And you can interpret this as how efficient you are in producing anything, regardless of labor investment or capital investments made. And we will produce carpets. Carpets are amazing. You can find them in every old-fashioned house. And to produce one, you might want to go to a factory where there are workers glittering every bit of this fancy carpet. And we will have a couple of those workers. They will invest their labor to produce carpets. Our workers are different, and some of them produce very large carpets that are like full wall sized carpets. And other workers will produce small sized carpets that you place on the floor near the entrance. So this means that the daily production or weekly production of those items would be very, very different. And this is reflected in total factor productivity. Large carpets will have little total factor productivity. Small carpets would have larger factor productivity. Our workers don't interact with each other, but still produce large amounts of those carpets in a year. And so we can collect data about their productivity. Sometimes they put a lot of their efforts a week and produce a lot of items. Sometimes they don't have a lot of purchases and don't need to work very hard. So we have a lot of observations with different labor investments. If we just pull every data on one plot, we will not see any dependency on how many carpets are produced a week. But we know that there are different groups. And if we stratify our data by our workers, we will see that, oh, really? The more labor is invested, the more carpets they produce. This will range from time to time, but yet we will have this dependency shown clearly. Sometimes this paradox is called Simpson paradox. When you pull the data, you don't see any dependency, but when you introduce groups or so-called hierarchies, you now clearly see the differences. The general approach to accomplish this model, or any other model that will include groups or hierarchies or any other stratification, is to start with a simple model that don't take into account any of those complications. If you have a lot of groups, start with one. If you have a lot of groups and you think that they can all be combined, start with pooled data. And when you make sure that priors are well specified, you do checks, then you are good to go to introduce yet another complexity, the hierarchy. Without this step, stepping into the ground of hierarchical model might be very not dangerous, but it may become misleading when you have a non-working model and you don't know how to fix it. But if you have a simple working well model, then you can add a bit of complexity you understand. That's how we will go through our example. We will start with a simple model and introduce priors so that we can interpret everything about this model and priors. And our model in general looks like this equation. Emitted with emitted noise, it is just an exponential model of production. We will need some priors to be set for A, for beta, and for the noise factor. The original parameterization that includes an exponent might be very challenging to deal with. And people usually reparameterize the model in a log-log model, and that will help a lot with estimating the parameters. If somebody is familiar with what is econometrics, then in econometrics, you might encounter these types of models when you have logarithm on the left-hand side and on the right-hand side. So a unit change on the right-hand side is interpreted as a percentage change on the right-hand side that translates into percentage change on the left-hand side. So everything will be actually on the relative scale, even noise factors. We can now rewrite our model into something that resembles the notation of a Bayesian model. When you have an observation simulated from normal distribution with some mean estimate, that would be our model, a log-log model, and the standard deviation for noise. An open question is to how to get all those priors. We will start with a simple one, a prior distribution for beta. And I say this is relatively simple because you know for sure that elasticity for labor productivity and elasticity, for those who are not familiar with it, is the translation of percentage change of labor to percentage change in production. Of course, it can be negative. It can't also be very large. It actually can't be larger than 1 because, well, it would be very strange when your labor investment skyrockets the more you invest. So it is actually bounded by 0 and 1. And there are a couple of distributions that reflect this knowledge. For example, it can be uniform distribution, beta distribution. There is nothing special in any of these distributions. They should just reflect your prior knowledge. You can set beta in the way that it either zero avoiding or vice versa, very large zeros. It can be logit normal that always avoids boundaries. It can be uniform if you don't know anything about the problem, and it would be a special case of beta distribution. It can be a simple version of beta distribution that is called Kumara-Swamy. And well, you can freely choose between beta and Kumara-Swamy, or whatever you like more. And whatever you choose, it is a very good idea to visualize first what is your prior distribution for at least one parameter set. I like logit normal more just because of the parameterization. I like normals. Everybody does. And we will go with the logit normal distribution just because it's your choice, and the more convenient you are with your choice, the better for your model. If you can interpret better another type of distribution, then you can go with another choice. It's all up to you. If you're writing a paper or a technical report, it's a good idea to document every step of your prior choice. It can be a snippet, it can be a little comment about your prior knowledge, anything. It will be very helpful for colleagues that will review your work and discuss it later. All right, we have set up the distribution for beta coefficient in our model, the elasticity for labor factor. And what would we do for the rest of them? For example, for epsilon, the noise factor. And just rule of thumb for any noise factors. It is usually a distribution that is zero avoiding. It is a rare case when you have a model where you have literally zero noise. And it is highly unlikely that you have sigma very close to zero. So this restricts the distribution set for what you can choose for prior. It can be log normal, it can be gamma distribution. They all share this property for zero avoidance. I will go with log normal distribution. And actually, it is quite unclear at this step what should be the parameterization for log normal distribution. What should be the mean? What should be the sigma of this log normal distribution? And in our case, epsilon is the noise factor. And as I said, in the log-log model, it is on the relative scale. So when we have epsilon is equal to 0.1, it translates to a relative error of order 10%. So setting epsilon is setting these relative error bars in our model setup. And this is very useful to know when you're working with other types of models, when your observation is on the log scale and you're unsure about the error term. So if your observation is on the log scale, then error term is also on the log scale and interpreted as relative error. With those priors set up, the one is left. And this is total factor productivity, or in other words, the intercept of the linear regression. If you want a fancy look, then you can call pm.model to graph these and pass your model and you will see the fancy description of a model, which is quite useful if you have a very large model. So you can see the dependencies between the parameters, you can see the cages that take into account the either hierarchy or number of observations or other dimensions. So let's go to the more complicated prior. And on the first glance, it's very challenging to even figure out what should be the prior for total factor productivity. But yet we know something about the output. We know that it should be in some reasonable range for how many actual carpets are produced by workers. And this is the step when we can link the parameter that is inside the model, which is very hard to get, not necessarily the intercept, with the output. And in this example, we know that both the output and the intercept, they are positive. And if we have a domain knowledge about the range of outputs, then we can infer the acceptable range for intercept or other parameters. And let's say in our case, we have knowledge that in a week, a manufacturer can produce orders of 10 carpets. That would make at least some sense. If we don't know, then we can use prior predictive to compare what the model predicts to what the actual observations we have. And prior predictive is the simulation model for our observations. Given we have literally no observed data, we have no likelihood. It's just taking inputs, our priors, and simulating what would be the output given our assumptions, the model, and everything we put into priors. Sometimes setting priors is a very tough work, especially if the parameter is not the intercept. You have to iterate over setting a parameter and looking to the prior predictive. And let's say we don't want to think about it and just set the intercept to be log normal. That is a common case in modeling when we don't know anything, just set the uninformative prior or whatever comes in mind. And if we make the simulation of prior predictive, we will see how dramatic is our mistake. Given our assumptions, prior predictive will indicate that the probable range of manufacturing carpets is from 0 to 800, and that makes very little sense. Even if we don't know if we don't have the domain expertise, that's very unreasonable amount of items produced. And given we have this picture, there is a lot of information we can get from it. We see that there is a lot of dispersion happening in the model. It can either come from total factor productivity that widely ranges from in the unreasonable range, or it can be the error term that is very non-restrictive at all. So we can try to figure out what are the better choices for intercept and for for the error term, so that we can have the observations at least in the range that we actually expect. If we play around with those parameters, we will come up to something that will probably resemble this picture. The actual parameters for log normal, for epsilon, and for intercept, they might be different, but at least they can put the prediction model, the prior prediction model, into the range that you can interpret. And in this case, we can see that the prior predictive will put the observations somewhere between 0 and 25. To do this, we should follow the iterative process to get no astronomical speeds or distances, not to get some black hole density estimations, and in our case, no superpower whoppers. So something that we can still interpret, and this is usually the observations. So it is if we don't understand our observations, what we're doing with Bayesian modeling. So at least something that is in the observation model we can interpret very relatively good. And if we have a very weird predictions from prior, then we can say that something is wrong with the model itself. And this is why we use prior predictive everywhere to check if the model makes sense or not. So there is a question in the Q&A. Is prior predictive a probability distribution? And I say yes, it is a probability distribution of the observational model given no condition on data. If you have a linear regression, you still have this pair x and y, and you exclude the second item, the y. You just have the inputs in the linear regression. And everything else is unobserved. You don't have anything, just raw inputs, your priors. And this is enough to simulate the predictions without anything actually observed. So data is like the reference to your prior predictive. It is not used in simulation, and it shouldn't be treated as the objective. When you simulate your prior predictive and you're trying to make it look exactly like the prior, like your data, this might lead to a mistake when you overly rely on data. If you're familiar with machine learning terminology, you can make the equal sign between overfitting and fitting your prior predictive to data. Ideally, you don't even look at the data when you do this simulation, but I agree that sometimes it is really not possible to get into every domain-specific problem and understand what is this parameters reasonable scale. So yeah, in such situations where I work with many projects at once, my rule of thumb is get at least something that is on the same order as data. So if my observations are at order of thousands, and then having 1,000 plus minus 30% from prior predictive should be considered enough. Everything else I think it can be considered as overfitting and over-reliance on data. And it's often a good idea to consult to someone else who is more familiar with data or problem and just ask a simple question. Hey, what is the reasonable range for predictions for carpets produced, for temperature outside, anything? And given you have an answer to this question, you can just put it into the model and adjust your prior predictive to this bit of information. This would be much more useful than fitting to data. And here we go, pressing the sampling button. After the sampling, we should see and look for the well-behaved chains in Hamiltonian Monte-Carlo. We should look for no divergences. We should look for no multimodality in the posterior distribution. And if we have some of these problems, then should go to resources that explain how to deal with these problems. And in this session, we will try to figure out what to do with divergences that come up from bad parameterization. But right here, we don't have this issue, and everything looks very good. No divergences, no multimodality, nothing. Sometimes it's also a good idea to plot the posterior distribution to prior distribution to see if we were good at guessing. And yet this plot is not very actionable. It would reveal how good we are at our intuition. After we get a well-behaved model, we can add hierarchies. And hierarchies, in our case, is the total factor productivity. So the larger the carpet, the more carpets per week are produced, and vice versa. Oh, the smaller the carpet, pardon. And this would be the model with variable intercept. And this is what we should place prior for. Hierarchies is a very, very broad term. They can be any countries, regions within countries. That would be even multi-level hierarchy. It could be user groups, splits by profession, other groups, many things. They can also be combined, so different subjects like share age groups and profession, but some subjects might not share the same age and profession. Every such combination is just treated hierarchy. Even if you estimate treatment effects, this is also an example of a very, very simple hierarchy with just two groups. Hierarchies might be very, very domain specific, like time-dependent effects when subjects are related to each other with time scale. For example, it could be the same subject, but estimated at different time points. Or same subject placed, but estimated in different locations. When you have different relation, depending how far are you from the original observation, for example. Our case is very simple and doesn't take into account complications with geolocation and time dependencies. They're just independent. There will be a future session when we discuss the spatial hierarchy with Gaussian processes, but let's focus on a simple case. If you're familiar with econometrics, then you might recall there are different types of panel data and models you can apply for panel data. And this is very relevant to what we're doing with Bayesian model. When we think that all groups are independent, like literally there is no difference between all of them, then we have a pooled model when we have a common intercept shared between all the groups. Sometimes we think that groups have significant differences, and in this case we call this model fixed effect model. This is the case where we have a couple of countries, regions that are very different from each other and doesn't necessarily share all the properties of the model between them. And these intercepts are estimated independently for every country or every group that is in the experiment. And the last one is random effects model. This is the model where groups are considered to be different from each other, but not very significantly different. So we can say that they're randomly different from each other. And that's why it's called random effects model. Now, this is different from fixed effects model in the way that there is an additional error term that is shared across all the observations within the group. And this additional error term is UK. You can find this in literature. And the common assumptions for those error terms is just having an expected error at 0. When we go into a Bayesian framework, this all becomes very familiar if we group the random effects model properly. And we place the error term, the additional error term, very close to the intercept and treat it as a group intercept. And alpha, in this case, can be interpreted as population mean and alpha k as group mean, group intercept. And there are two challenging parameterizations that you can find in Bayesian analysis. One of them is centered, another one is non-centered. They're very closely related to each other, and when you plot the prior distribution, they're indistinguishable, but they still behave very different in practice. In non-centered parameterization, the group-specific parameter UK is said to be the group difference from the global mean, from the population mean. And sigma, that is used in both parameterizations, don't mess it up with sigma bar. It's just sigma. This one, if you see the cursor, and this one is the measure of group differences. And it's a measure for how different are groups within the population. So if sigma is very close to 0, then we're the case with pooled model. So when alpha, the intercept is shared across all the groups. When we have small sigma, and small is, again, very domain-specific thing. When we have the small sigma, we have random effects model. And with large sigma, we allow groups to be very, very different from each other around the population mean. And this is the case with fixed effects models. It's very similar behavior when every subject, every group is considered to be an individual, very different from anything else. And if sigma is infinite, and then it's clearly the fixed effects model, and there is no domain knowledge about how far they can be from the population mean. But again, this would be a non-proper Bayesian model. And setting sigma to something specific will interpolate between all these cases. If we think that everything should be very similar, we can set sigma to be zero, like likable distribution that oftenly is close to zeros. And if we think that they shouldn't be necessarily similar, we can set the distribution that either avoids zeros or don't put very much weight to the region close to 0. If we compare the behavior of centered parameterization and non-centered parameterization on some toy examples, we will see that the behavior of HMC algorithm will lead to divergences in one case and not in other case. This happens because not disentangling the group difference from the model will lead to a situation where with small sigma, we have a very wide region where alpha k can appear. And with narrow sigma, the region is very restricted. And in HMC, there is a step size that in one case should be large, and in other case, the step size should be very small. And it can be both at once. So there is impossibility for the sampler to get everything from one region and everything from another region. So you either have small step size and you don't explore the region with low density region, or you have small step size and only explore the high density region that is funnel-like. When you disentangle everything, your distribution looks like a Gaussian, and it is basically Gaussian in the parameterization. And that's why the non-centered parameterization is in some way very beautiful. So geometry is very important when you think about parameterization, because the algorithm has assumptions about common step size across all the parameter region, all the parameter domain, any complication or violation of this assumption will lead to divergences and bad situation. You can have a nice read from Stan's guide about how to choose and set parameterizations and how to avoid such things. Another good reading, but it is much more involved, is from Michael Betancourt. He discusses not only the degeneracies of centered parameterization, but also, surprisingly, the pitfalls of non-centered parameterization. And in short, if you have a very informed posterior density, and that is called by very informed likelihood, you will still see the degeneracy, the funnel-like degeneracy. And in simple words, this case can be described as violating the prior assumptions to a large extent. But in most cases, the non-centered parameterization is the way to go. And it's a good suggestion to just start with non-centered parameterization. And if something is behaving wrong, then you can try centered parameterization as well, because it's very hard to predict if you will have very informed posterior density or not. So let's go back to our example and let's try to set up the hierarchical prior. At least we have the idea about the non-hierarchical model. We know the prior distributions for our error terms, about the beta coefficient, about the intercept. We know pretty everything about the model and that it behaves very, very well. When we go to hierarchy, we first need to decide which parameters we share across all the groups and which parameters and to which extent we allow to be variable between the groups. And then we debug. As a software suggestion, make it like a parameter. Centered parameterization equals true or false. That would be very helpful to debug the model and try different parameterizations. Here is how can we translate a non-hierarchical model to hierarchical one. And the key difference is in how we specify the intercept. So previously, it was log normal distribution with mean and sigma. And if we follow the non-centered, or if we follow centered parameterization, then instead of just mean, we place the population mean. And because we're dealing with log normal distribution, it will be the log population mean. And then we also specify the population sigma. And this is exactly the variability across all the groups. So if sigma is small, we have low variability between the groups. If sigma is huge, then we allow groups to be very, very different from each other. And for population mean, it's a very good idea to specify it just as it was in a simple model and see how it goes. Because if it works for a single group, then it is a reflection of an assumption that a population is just sampling from similar groups. And our initial group was just a sample from these population. For population sigma, it will follow the same intuition as it was with error term. How variable should be the differences between the individual groups. So if it is plus minus 10%, plus minus 50%, it will follow the same intuition to set this log normal prior. And again, this is possible because we are in the log scale domain. If we're in real scale domain, we will have the similar intuition, but with regular sigma in error term in population sigma. So plus minus 10, plus minus 15 from the population mean. That's how it would be interpreted. After adding reasonable variability for sigma, we can already try the model and see how it works with first parameter predictive or pre-predictive study, and then sample the whole model with HMC. That's it for today. And if you have some questions or maybe clarifications, you can put it into Q&A, and I'll try to do my best to answer those questions. If you want to discuss it even further, then here is the link to book a call or reach me out on LinkedIn. All right, we got some questions. The first one. How would you set correlations between parameters when simulating a prior predictive distribution with PyMC? In the case you know the two parameters x and y have correlation of 0.5, and you want to constrain your model. Well, that seems like the two-dimensional Gaussian would at least to be helpful to do this, but I'm not sure that it is something you're looking for. And if you can clarify your question, I can be a little bit more specific. But if you just want to model correlations between two parameters, then correlated multivariate normal is something that can help. I think I'll wait for clarification for this question and go ahead to answer another questions. From your experience, what is the number of max hierarchies we can work with? Well, I've worked at most with two-level hierarchy, where the simple case is there is one level hierarchy. There can be a lot of groups, maybe tens, maybe thousands, maybe even more. And one level hierarchy is not that challenging because you just switch between centered and non-centered parameterization, depending on how many subjects are there in the groups. And if there are low sample size groups, then the rest groups inform this case. For two-level hierarchy, things are a little bit different. And the degeneracies for this funnel, they explode like dramatically. So it is really challenging to get into this field. On the other hand, there might be types of hierarchies that are kind of disentangled between each other. And you can treat it as two-level hierarchy is country level, then region level. And another type of hierarchies is when you have country level and, let's say, ages. So they don't necessarily are subsets of the same group. And in this case, when you have age and country level segregation, then it is still the case when everything is quite flexible and it is possible to fit a model with large number of groups in both cases, but the computational time will grow the more groups you have. And sometimes it can become prohibitively slow. But this level of prohibitively slow is quite reasonable. So in most cases, you are just fine with getting a couple, like 10 different small size groups. But if you have 10 groups with 10 types of hierarchies with thousands of groups within each other, then things are a bit slow. With the hierarchy, next question is, with a hierarchical model of similar countries where mainly the scale is different, would you recommend using a pooled model? So similar countries, scale is different. I can only make guesses what is scale, the scale of countries using pooled model. I think the hierarchical model will still be useful in this scenario. At least it can be less restrictive to what is the aggregation for, what is the population standard deviation. But I found that it is very common that there is a lot of data for one country and small data for other country. This is where the hierarchy stuff can be useful. Otherwise, the added benefit is lower. Another thing you can try is the type of hierarchy where you don't treat everything as independent, but you have a latent Gaussian process that depend on parameters of country size, area, and something else. So the intercept is similar to those countries that are closer to each other in this metric space, and different for those who are treated differently. So there is something to experiment with, from independence to something structured for hierarchies. Okay, next question. Regarding the fixed or random effects, we have panel data, meaning we take measurements from the same subject multiple times. Doesn't it violate the assumptions of independence? Well, on one hand, it does. On the other hand, we might ignore this in our application. For example, if we don't assume that one observation affects another observation, then they are independent in the way that we want to incorporate in the model. But if one observation influences another one, then we might want to add an additional bit of information to the model. For example, we can have the correlated error terms that are similar in close time periods, or something like this. And there are techniques to take this in account. But in most cases, this is often ignored, and we usually know when we need to take these error terms in account. It is another expertise to put into the model, or to drop it if we think that it is not so important. But answering the question specifically, yes, it does. It does break the assumption of independence. Next question. Do you recommend some resources where we can get an intuition on what probability distribution is more appropriate to use, besides using Poisson for counts, better for probabilities? I don't have a resource in mind, and I'm actually thinking of writing something like this. To answer this question immediately, as I do it, I go to Wikipedia. Yes, I use Wikipedia to look some specific nuances of distributions. And this is very helpful to make an educated guess. And things I often take into account is zero avoidance, boundaries, flexibility for shape and scale. Sometimes I need to control both. And I'm specifically looking for a distribution that has both properties, or exactly one property that I need to control. So if you're looking for a distribution that is zero avoiding, then you're looking for distributions like log normal, gamma. If you're looking for distributions that want to get closer to zeros, then I look other specific distributions, and then you have requirements for the parameter set for this distribution, for distribution of your choice. Whether you want to control shapes, scale in addition, or something else. This way to judge about our distributions is very helpful to make a choice. And it can be either prior distribution or likelihood distribution. It doesn't necessarily matter. The next question. Is it possible to estimate parameters in group A and use them in group B if we have high confidence in group A? High confidence in group A. I think it is possible, and it would be reflected in additional parameter, the error term. We can make error terms to be hierarchical in the sense that there will be sigma for group A and a different sigma for group B. And we can set one sigma to be greater than another by some factor. And this will implicitly weight the observations in one group to be more accurate than in another group. And it will also lead to a redistribution of information gained in other parameters. So coefficients in the linear regression will get more information from group A with small error term rather than from group B with greater error term. So there is some flexibility in how you can add hierarchies. So it's not only about intercepts or slopes, it can also be the error term. So there are no open questions. If you have more, then don't hesitate, text them.